All right, good morning, kids. Let's see how this goes. I'm new with this technology, so bear with me here, but hopefully this works out. NMSI packet, answer key. Already posted some of the answers, or all the answers written out on Google Drive. So if you need to see how I did them live and have me explain through it, then this is the video for you. So we'll start with number one, and it kind of number 1 and 2 kind of deal with the same graph. So if I look at it here, I got, this is a force by displacement graph, and it kind of looks like that. And it asks, which of the following would be most likely to produce the force shown in the graph? Choices are A, a string tied to a falling mass, a stretched spring, a magnet placed in the direction of the displacement, and kinetic friction. Well, we know kinetic friction is not it because it's going to be a constant. A magnet placed in the direction of displacement, that would be the force should go up, because as you get closer to the magnet, the force should go up. Our force here goes down. A stretched spring, the key to this is it does not say what direction the displacement is. So how you know it's going to be B is because you could have it away from the equilibrium, in other words, a big force, and have the displacement towards the equilibrium. In other words, moving to a less force, or if it goes all the way back to equilibrium like we see here, the force is actually going to be 0. So that's why the answer for 1 is going to be B. Number 2, so I'll keep this up because it's the same graph, as the amount of work done by the force in displacing the object 2 meters is most nearly. So you have to remember from your work and energy unit, that the area under a force by displacement graph is equal to the work done. So if I have a force by displacement graph like I do, I just need to find this area. It's a triangle, so work area. All I have to do is area equals 1/2 base times height. That's triangle. Area equals 1/2. Base is 0.2. Height is 20, and I get 2 joules of work. Answer. All right, so that's 1 and 2. I'm going to clear this guy out. All right. Number 3, it has a drawing. A simple pendulum is constructed by a string length L. So this is for number 3 and 4, so I guess I'll draw it. It has this. It has, this is spot 1. This is spot 2. This is spot 3. So that's 1. Oh. That's 2. That's 3. And we have that this distance here is y. So it says the speed of the pendulum bob when it's position 2 is most nearly this. So if you read the problem, it says that there's friction and drag. You don't include that. So there's no outside forces acting on this pendulum. So what I can do is I know the law of conservation of energy holds true. So energy total at 1 has to equal energy total at 2. Now, I think of energy at 1, at that point, it's the highest point. So at that point, it is actually not moving. So it has 0 kinetic energy. So energy at 1, I know, is just potential energy, which is equal to mgh. All right. Now, the energy at point 2, if I've set that to be my height equals 0 point, because my height is going to be equal to y, so I can literally just say this is y instead of that. I'll get my thing back up there. There we go. All right. So that's my 0 point. I know that at point 2, it's not going to have any height, so it's going to have 0 potential. It's going to have all kinetic. So kinetic at 2 equals equals 1/2 mv squared. I know that this is what's happening here, so that's the total energy, that's the total energy. I get mgy equals 1/2 mv squared. Basically, you can solve for v there, use algebra, get it all over there, and I get velocity is equal to the square root of 2gy. And your answer there is going to be, what is that? B. All right, so let me clear this. All right, so same scenario here. Let's see what question 4 asks. It says, which one of the following graphs best shows the total energy of the pendulum bob as a function of displacement? Well, using the fact that we just used to solve that, we said energy total at 1 equals energy total at 2. We can also say it equals energy total at, because there's no outside forces. So if our energy total isn't constant the whole time, it's going to have to be the graph that looks like this. Constant energy looks like that. So answer is, all right, pretty easy here. So let's clear this guy. All right, 5. A block is attached to a horizontal spring and put into simple harmonic motion with an amplitude of 6 centimeters. When the block is 3 centimeters from the equilibrium position, what is the ratio of total mechanic energy to kinetic energy? All right. So let's look here. This one, let's start at, so this is number 5. Let's start at 6 centimeters. So at 6 centimeters, okay? At the amplitude, we're talking about a spring, right? So at 6 centimeters, if that's the amplitude, we know that it's not moving, right? At the maximum point, it's going to stop, and then it's going to continue back in the other direction to continue the simple harmonic motion. So what we can do here is we know the energy total at that point is equal to just the potential energy of the spring, which is also equal to 1/2 K. X is going to be x squared, but x in this case is going to be the amplitude squared because we're at 6 centimeters. So if I kind of plug in there, I know, here's what's going to happen. You're going to see me just kind of ignore the 1/2 and K because it's the same spring. So the ratio of that playing into the final answer or the approximation, so I'm going to do approximately around 36. Because the only thing that's going to be changing is the value of A, X, stuff like that, or velocity. So that's kind of what we got to look at. So now if I look here and I go at, where does it want, 3 centimeters? Okay. I know it still has, so energy total is going to be equal to potential energy of the spring at that point plus the kinetic energy at that point. So because it's going to be moving, because it's moving backwards or it doesn't matter which way because it's harmonic motion. But here's the key: I now know that it's 36. What I can do is, if I can find how much potential energy it has at 3 centimeters, I can then find, because I know energy total is equal to that, I can then find how much kinetic energy is that, and I can compare the ratio once I do that. So I got, I can kind of do the same thing here. I got 1/2 K, and my X this time is 3 squared. So what I get here is 9. So I basically get 36. This is 9 because I did the same thing. I forgot about the K and 1/2 because it was over here already. So I get 9 plus whatever kinetic energy there is. So the kinetic energy has to equal approximately 26. 27. So if I look at the ratio, it wants the ratio of total mechanical energy to kinetic energy. So my ratio is going to be 27 over 36, which simplifies to 3/4, which is answer D. Good. All right. Number 6. Let's keep on rolling. So it says, what is the total energy of a 1 kilogram object on a horizontal spring with a amplitude of 0.1 meters and a frequency of 5 hertz? All right, so the first thing you need to remember here is that frequency is equal to 1 over the period. So what I'm going to do is basically take the inverse of the period equation for a horizontal or for a spring system. So basically the frequency of that is going to be just the inverse, 1 over 2 pi, because it was 2 pi. And I'm going to flip what's in the radical. So it's K over M. All right? So because frequency is equal to 1 over the period, I can then rewrite the frequency of a mass on a spring system to be the inverse of the period. So what I'm going to do here is I'm going to solve for K first. If I can get a K value, that would really help me here. So let's see, I just want to move all this stuff over. So I get F 2 pi radical K times M. I square both sides. I get this quantity squared equals K over M. So I multiply by K, so I get this quantity is still squared, 2 pi squared times M equals K. All right, so I can plug in there. I plug your numbers in. I'm not going to plug the numbers in. If you want to see it, it's on the other one. You get 100 pi squared, just the pi squared. So that's our K value for the spring. Now what we want to do, we want to find the total energy of the system. Is that what? Yeah. So it gives us the amplitude. So again, at the amplitude, we know velocity is 0. So kinetic energy is 0. So if we can just find the potential energy of a spring at that point is 1/2 K 100 pi squared. It's 1/2 K x squared. So I got 0.1 squared. So I look at this, I can solve. Once I solve, I get 1/2 pi squared. And that's going to be answer B. So again, the key is understanding that at the amplitude, the velocity is 0. Therefore, the only energy it has is potential energy. All right? Let's go to number 7. See what it says here. All right. So it says a mass, so number 7. A mass spring system is set up so it exhibits simple harmonic motion with an amplitude of 6 centimeters. How are the total mechanical energy and the system's maximum displacement affected if the amplitude was doubled to 12 centimeters? So let's look at total mechanical energy here. We know that, again, if we're talking about amplitude, let's look at the potential energy. So U equals 1/2 K amplitude squared, so that takes care of that. If I double the amplitude, it says I'm going to increase it 6 to 12. So if I keep going here and I go 1/2 K A squared, when I square that, let's see, I get 1/2 K 4 A squared. So it's literally going to change this by a factor of 4. So in the first column, it's going to be 4 times larger. So that eliminates C. I mean, that's pretty common. We do that all the time with forces of gravity, stuff like that. So now if I look at maximum displacement, I look at my simple harmonic equation here. It really doesn't matter if you're using sine or cosine here because it's just displacement. A cosine 2 pi frequency time. Now, if I look at that, what happens if this gets doubled? If I go that, well, pretty straightforward. It doubles, right? Because you're adding in a factor of 2. This is the same. So if I look at the answer sheet here, 4 times larger, 2 times larger, my answer should be B. All right. 8. It says mass spring system A has a frequency FA. Mass spring system B has a frequency FB equals 2FA. Both springs have the same length and the same spring constant. How are mass A and mass B related? All right, perfect. So you gotta remember that frequency is 1 over the period, just like we did in the other problem. So that tells me is if I can look at their frequency to be this 2 pi A. Yeah, that's what I'm going to use here. Okay, so I know this frequency of B equals, this is what it gives you in the problem. Where's it at? 2 frequency of A, right? They give you that. They're saying that frequency A or frequency B is 2 times the frequency of A. So let's go ahead and plug in here. So I know frequency of B is going to equal this. I know this is going to be so basically what I'm going to do is kind of solve this. Right away I can get rid of these because they're going to cancel each other out. K M equals 2 K M. I should denote that this is B, massive B, massive A. That's going to be different. So what I'm going to do here is I'm going to square both sides to get rid of the radicals. So I get K M B equals 4 K M A. And then I can basically solve this, right? K's cancel out because it's the same. So the key to this is the K is going to be the same because it's the same spring. So I can rewrite this as 1 over MB equals 4 over MA. I can do a little cross guy and say 4 MB equals M. Let's see, is that answer? Looks like it's going to be D. Answer. Let's move on to number 9. It says, let me clear this. Pendulum in a clock increases in length slightly as a clock's temperature increases. How will this affect the clock's timekeeping ability? Well, all right, so what we have to do is look, so you're looking for a period. So the clock uses it as the period is going to be equal to a second, or however the clock keeps time. So if I'm changing the length, so I increase the length as the temperature increases. So I have to see what increase in the length would do to the period. So my period is equal to 2 pi L over T. So if I get a bigger number here, so my number is bigger, my number is going to go up, that gives me a period that also has to go up, right? Because this stays the same, this stays the same, all right? So my period is going to go up. So in other words, it can be longer than 1 second. So what that's going to do is it's going to swing slower, and therefore the clock is going to run slower. So the answer is A. All right, let's move on to 10. Number 10. A simple pendulum on Earth's surface, a distance r from the center of Earth, has a period of 1 second. The pendulum is moved to a distance of 2r from the Earth's center. What is the period at the new location? All right, so we know that, let's look at Earth's surface. That's pretty easy. We know g there is the same. So Earth, you know, the period is going to be equal to 2 pi. So now if we look at 2r, this kind of goes back to your universal gravitation chapter. So I got to remember that force is equal to big G m1 m2 over r squared. Now, if I want the acceleration due to gravity, in other words, G, excuse me, I got to remember that force is equal to mass times acceleration, and the acceleration in this part is my acceleration due to gravity. So let's keep going here. So this is why the acceleration due to gravity is the same for all units, for everything, right? So everything has the same, falls the same. Remember the feather and bowling ball video, where the feather and the bowling ball falls at the same rate? This is why, because the mass cancels out here, so it cancels out one mass. The only mass that comes into play is Earth's mass. So I know the acceleration due to gravity is big G m squared. So in this problem, you are, what does it say? You're doubling the radius, right? So if I go G, big G, m, 2r squared, gravity actually decreases by a factor of 1/4. Right? So that's our normal gravity if there's there, but then we have to remember we got this factor out there. So G is basically by a factor, new G, this is G prime, whatever we want to call it. All right, now we got to use that in this equation to compare. So this is separate. Let's separate that. So now this is still 2r over here. T equals 2 pi L 1/4 G. So in other words, I could just rewrite it as T equals 2 pi 4L over G. I simplify that and I get, well, I can take the square root here. I'm running out of room. Let me erase some of this junk. Hopefully you don't need the gravity part anymore. All right, so if I continue here, I square root this, the 4, because it's a perfect square, so I can go T equals 2 pi, I bring the 2 out times 2, and I'm left with LG, so I multiply here, I get 4 pi square root LG, so I see that it increases by a factor of 2, so if it increases by a factor of 2, in the first period was 1, so 1 times 2 would be 2 seconds, so the answer there is going to be B. What number was that? Was that 10? All right, let's go to 11. Clear this. All right, so next it says a block of mass 3 kilograms is hung from a spring, causing it to stretch 12 centimeters at equilibrium, as shown above. So I'll draw this real quick. We got spring, nothing on it. then you hang 3 kilograms on it, and it stretches a distance of 12 centimeters. Next thing you're going to do is hang, not 41, uh, 4 kilograms on it. All right, so how far will the 4 kilogram block fall before its direction is reversed? So let's look at this here. What we need to do first is find the K value here. And really what you're going to need to do is look at the 3 kilogram block. So in this case, we're looking at this equation, Hooke's law, right? The force of the spring in this case over here is going to be equal to the weight, right? Because the only thing that's pulling it down is the weight. The spring is pulling it up. So I got weight pulling it down, spring pulling it up. It's not moving, so therefore those forces have to be equal. So I can rewrite this as mg equals kx. My mass is 3, gravity is 9.8. All right, they use 10 to make it easy. 10 equals, K is what I'm looking for, X is 0.12 meters. So when I do this out, I get 250 meters, and that's my K value. So now I know it's the same. All right, I know it's the same. So let's see what I did here. All right, so I'm going to actually erase this. I hope you're good with K value. I need a little space here, so I'll need to erase. All right. So now we're going to switch to the 4 kilogram block. All right, so we know it's released from rest, and we know that. Actually, let me draw two to help you understand this. So it's released from rest from here. All right, this is my reference point where it's going to be 0, and I'm going to call this my height. All right. So what I need to do is I can figure out that initially, so at the start here, if it's released from rest, the only energy it has is gravitational potential energy, which is equal to mgh in this case. All right, we're trying to figure out how far it's stretched. So if we set this point to be reference point 0, it still has a velocity of 0. Now it has a gravitational potential energy of 0, but it has potential energy of spring, which is equal to 1/2 kx squared. So because we know energy total equals energy total, I can say that mgh initially equals 1/2 k, and actually think about how far it's stretched. If it starts here and stretches down, my x is actually going to be the same distance as my height. All right, so what I can do here is I can plug in and solve. I know my mass is 4, my g is 10, my height I don't know. 1/2 k is, what was it, 250 h squared. So I go ahead and solve that. 40h equals 125 h squared. I kind of divide over here. I get rid of the h. So I got 40 equals 125 h. And h equals 0.32 meters. Therefore, what is that? Answer is D. Yeah, answer All right, good. That's 11. Let's go to 12. Clear. 12. All right. So it says a sphere of mass 1, which is attached to a spring, is displaced downward from its equilibrium position as shown and released from rest. A sphere of M2, which is suspended from a string length L, is displaced to the right as shown above, released from rest, so it swings a simple pendulum with a small amplitude. Assume that both spheres undergo simple harmonic motion. Which of the following is true for both spheres? So this kind of goes back to just kind of concepts here. So if you look at A, you're gonna figure out that A is the correct answer here. It says the maximum kinetic energy is attained as the spheres pass through its equilibrium. So if I look at the spring, as that spring is stretched down, right, it stores up potential energy. As it's moving up, remember we said it's going to keep accelerating because the spring is still going to pull it up, accelerating until it reaches the equilibrium point. There's no acceleration. In other words, maximum velocity, because once it travels past equilibrium, the acceleration is going to be the opposite direction. So at equilibrium, from that point on, it's going to slow down. So we should know that if it's the max velocity at that point, then it's going to have the maximum kinetic energy. And then if I look at the pendulum, right, that's a little bit easier. Right here, it's at 0, right? Oh, what am I doing? I can draw it, right? Right here, the velocity is 0. At this point here, it has swung down. Once it passes this point, gravity's going to be pulling it downward, right? The acceleration vector is going to be downward. So it's going to start slowing down right after it passes that equilibrium point. So just like the spring speeds up until here, 0 acceleration, but once it hits anywhere past there, it's going to start slowing down. Therefore, max velocity is here. That's why the answer should have drawn the other one too, but my bad. 13. All right, let's see. Oh, it has to do with both of them, so I'll draw it. Clear. So this is 13. So you got a spring with a box. This is 0.3. This is 0.2. And this is 0.1. So no friction. The min and max are at 1 and 3. The graph below represents quantities associated with oscillations as a function of the length x of a spring. Which of the following graphs best shows the total mechanical energy of the spring system? All right, so this goes to total energy again. Remember, if we're doing it without friction or anything else, the total energy is conserved. So right away, we should know that the answer to 13 is going to be E, because it gives us that total energy is constant. The total energy of that system is constant. All right, so 14. Which of the following graphs best show the kinetic energy of a block as a function of displacement? So we're looking at kinetic energy here. What we know about kinetic energy here is this max velocity, right? We just talked about that in number 12. Here, our velocity is 0. What the heck? Our velocity equals 0. So we should know for sure the middle point and end point of the graph, right? So if I draw this graph here, I got 1, I got 2, I got 3. The end points are going to be 0. This is going to be the maximum. So really, there's only 2 graphs that can do that. We just got to figure out if it's a sharp guy, like this, or curvy guy, like that. So when we think about it, um, the force here is going to vary. All right. And if you see, this is kinetic energy. So as it gets closer, the change in velocity is going to be less and less and less. And if you look at that, if you look at the sharp one, that looks like a constant acceleration, right? Constant acceleration, because the velocity is going to change at a constant rate to give you straight lines. But if you look at D, the velocity gets decelerates and accelerates at a changing rate, right? Because that's how you get the curve. And that's what's going to happen with that spring. Like we said, as you get close to equilibrium, the force gets less, acceleration gets less. That's why it has to be that one. So our answer. For the sake of not making the videos too long, I'm going to do the free response separate. So that's it for the multiple choice. Hopefully I get better at this as we go along. So let's figure out how to stop this.